So I hope I'm audible. So let me use this and share it today. Let's see. Take it here. So welcome all to the third session of third live interaction section for the PMRF course on applied numerical methods. Um, I'm Shrey Sahai Gupta. Um, I'm the PMRF Prime Minister Research Fellow Teaching Assistant for this course. I'm a doctoral student at Indian Institute of Science, Bangalore. Let me just quickly start by a little bit of my introduction for people who are seeing these videos for the first time. Um, so I'm Shrey Sahai Gupta. I'm from Agra. I started my PhD in 2021. You can contact me on this email if you ever need some help. Um, and because someone has joined, if you have any doubts or any comments, please feel free to pause me and discuss those while I go with my stuff. So, before we get started with what we today's content, something which we'll continue from our last lecture, let me quickly give an overview um, of what we had been doing for the last few uh, sessions. So let me open this Jupyter notebook which I used for the first class. Hmm, Just give me a second. Hmm. Right. So the first lecture was a little bit of a glimpse to applied numerical methods, something that we saw, let it load, something that we saw very early on in the lectures or our interactions series, that people were more or less interested in application methods. Um, Finite approximation methods, and that comes under the category of solving differential equations, be it ordinary differential equations or partial differential equations. Um, the mathematics of the two are a little bit different in the sense that uh, partial differential addition of extra variables in PDEs add certain characteristics uh, to differential equations, certain distinct characteristics to a differential equation, and then it starts differing heavily from an ordinary differential equation. And so the two are treated differently wherever applicable, and mostly and obviously in applied numerical methods. So that is one thing. Um, so um, where do we see ourselves essentially? So week one was again a little was not very heavy. The It involved course instruction. So the first session also was a little bit glimpse into applied numerical methods. We saw that, as I was saying, finite approximation methods were the matter of interest for a lot of students. But to even get there, we need a certain prerequisites, which we are going to cover in the next few weeks. So that is something that I discussed. That the first thing to note there is system of linear equations, solving an eigenvalue problem, and then comes the stuff like interpolation, finite difference, and numerical differentiation. Numerical integration precedes solving ordinary differential equations. Those are indeed easiest to solve. But once you get into PDEs, there are other stuffs that you need to take care of. So there we might discuss a little bit on PDEs, but because the course is not um, centered or is not targeted at finite approximation methods, we move on to a more case study based week on modeling, non-dimensionalization, validation, and stuff. Then in the final weeks of our course, we'll be looking at more advanced topics which we can argue go a little bit outside the umbrella of numerical methods, uh, which is ANN, artificial neural networks. But to even go there, we need a little bit of primer into regression and optimization methods and gradient descent, stuff like that. The book that sir is following is Chapra and Canal, Numerical Methods for Engineers. You can look it up. Uh, then, essentially, the first week was about the square root algorithm, the Bakshakali formula, and the discussion led to the divide and average method, where we saw if we want to find the square root of some number, what we can do is take an initial guess. For any initial guess, we can find out the um, inverse inverse of that guess. Let me break the problem like this. So any square root, the square root of any number uh, multiplied by that number, multiplied by another. So uh, yeah, square root of any number multiplied by the by the number divided by the number you're trying to find. The so basically what I'm saying is, if your guess is a and if you multiply it by s by a, the multiplication gives you the number you're trying to find the under root of. So this s by a, let's call this operation as divide. So what essentially we are doing is by taking an initial guess, figuring out the divided number, and taking an average of it to find the best next guess. And we actually saw in the first lecture how it approaches the correct root of this equation, where x square equals to s kind of situation. And there we looked at Newton-Raphson, we looked at how this was kind of equal to Newton-Raphson. Okay, so this was week one. Week two began. Okay, before I go to week two, let me point out that the course content wise, uh, second week was not very heavy as well. It was intended towards a minimalistic introduction to computer programming. I thought this is a little preliminary in the age of AI. You can quickly look it up without needing any help from a teaching assistant. So we move to a important popular demand to discuss finite approximation methods. And in order to get there, we essentially wanted to look at the difference and implementation of finite volume, finite element, and uh, finite volume and finite difference methods. Um, what we saw was that uh, these are essentially used to solve differential equations. Mostly in a mechanical sense, you're solving conservation equations. Even in an electrical sense, I suppose it will be a conservation law only. But essentially, what you're doing is, in any continuum mechanics, you have conservation laws and constitutive laws. Uh, those locally established or written, presented, form the basis of your model, and those will inevitably be expressed in terms of differential equation. So we look at a differential equation to start with. Just to give it a physical picture, we looked at a 1D heat conduction problem, steady state. So one unknown, one variable, but unknown is a field rather than a single value. So it is a field. It is this temperature is distributed over X, and we are trying to calculate. What do you say? Well, in a single variable setting, field does not make any much difference because time, if you think about it, if any variable varying or evolving in one dimension will eventually be a field, so it does not matter. But let's say there was one unknown, which is temperature, and one known. But because it is a field, as I mentioned, we have to give two boundary conditions. So there were two boundary conditions essentially because the order of the equations was two. So there are two derivatives. If we integrate this equation, we know there is going to be two constant of integrations that we need to solve for, and that is required. That will be dealt or that will be found using these two boundary conditions. So essentially, we looked at a physical problem, and what we did was a small non-dimensionalization and stuff. We were at a point there where we had this form of the equation that we wanted to solve, right? And with given boundary conditions like zero at one end and one at another end. So we wanted to find this. Now, at this point, I started with the philosophy of a finite difference scheme, and led we led to a derivation, a small derivations where formulations of approximating the derivatives were substituted into our governing equation to so we had we arrived at so what we did was from this governing equation, this differential equations, we arrived at a system of linear equations, uh, and it looked like this. So AX equals to B kind of situation, and that we implemented in our computer program. But before I go there, let me also just quickly review or revise what was the essential physical picture of this finite difference scheme. So what we said was that rather than finding the function itself, so essentially we want to find a function, right? As I mentioned, we want to find the exact functional form of theta in terms of capital X. But the approximate method says that instead of finding the function itself, let's find its value uh, at a series of locations at starting so the locations that we are interested in, and these will be finite points, finite locations. So let me emphasize that so that this point is clear. So at finite locations, okay. So at finite locations, we are interested in, uh, or we can approximate any function by a series of its values at different points in the domain. Different at finite number of points in different points in the domain. That's okay. Finite locations. So that this was the essential picture. Taylor series approximation was used to different to make a make a approximation of the derivatives, and then there we went ahead and enforced it. So a finite difference scheme uh, enforces PDs only at interior nodes. So what essentially we did was that we interior node means that there will be boundary nodes also, right? There will be a node at the two boundaries. So we saw that in the finite difference scheme, we use the partial differential equations at the nodes except the boundary nodes, and there we had this form, and this essentially is a linear equation. There's a set of linear equations in theta i's where I varies from 1 to n minus 1. Um, and then we went ahead and we started writing this. Let me open that file. What where we did that. So 5th August. This was the last time we met. Today is 12th. So and essentially this was the most straightforward approximation method to solve PDs. This is a very go-to problem. This is a very go-to session. Problem is not very high end, and you want quick answers. So this is what we did. We represented or we formulated the finite difference scheme depending on the problem. We expressed this in terms of the system of linear equations. So this is what we have done in the program there. Let me just check if I'm recording or properly or not. Recording fine. Uh, I'm sharing as well. Let me check. Yes. So going back, so when we use this A and B to find out our theta values, and we saw that our theta values very well matched with our uh, exact solution. The interesting thing here would be when your discretization is coarse, your method is supposed to fail, or is at least it's not supposed to fail, but it might fail. Let's say that, but the failure is also not much. Let me decrease the uh, so here we can see at least for n equals to 3 or n equals to 2, we can quickly see that then now the point is not matching. So that's an important thing. We see that there is a visible error, at least for a very large number, for a very small number of discretization. But as we increase it, this discretization will go off. So we see that the error is quite small though now. But at very small discretization, this will fail. Uh, this will fail. Let me see. So it's supposed to fail, right? Let me think about it. So why is it failing here? Well, it's failing here. Let's look at what happens at 3. Yeah, because of our discretization is also very coarse, so there will be some errors. But as far as I remember, the nodes, the discretization should follow. So the errors, yeah, it's not zero, exactly zero, but small. So there will be small errors with finite difference scheme, even when there are so important thing to note here is that even though we were intending to find out the interior points values at interior nodes, the finite difference scheme still does not guarantee zero error at these nodes. Okay, that is an important aspect of this. It's an approximate method and it's a very straightforward method. Okay, because because the strength of the class or strength of people who have joined is not also high today. Let me not start with finite uh, uh, element method. Let me begin by finite volume methods. So that would be interesting as well. Another important thing to note when we when discussing finite volume methods that a lot of text actually avoid, like it does not avoid, forgets to mark the difference between finite difference and finite volume method. And this is where the paper that I had discussed, let me open this paper, uh, does this nicely. It clarifies the difference between the three schemes nicely, the underlying philosophy as well. So you can go through this paper. Upload it, and you'll find that so you what essentially I was saying is that what you'll see now, that again we are going to use Taylor series approximations for Taylor series approximation to estimate differentials. Similar to finite difference method, uh, here itself, you will have this, you had this Taylor series approximation. So people sometimes associate this series approximations with finite difference. And suppose that finite volume is also of that same category, but finite volume method actually uh, adopts or is based on a very different philosophy. And let's discuss that. Okay. So essentially what we have with us is, and I'll just quickly copy a few things. Yes. So essentially, the principle of finite volume is to consider small control volumes rather than looking at uh, interior nodes. So in finite difference, so let me point that out. So this was the picture in a finite difference scheme. But in a finite volume scheme, the thing is a little different. The volume is broken, or the space is broken into small volumes or small subsections. Okay. And how is it that how that happens is you break them into volumes. Okay. So what do I mean? Let me quickly align these two, align top. Okay. So command C, command V. So let me do this. Align top, distribute vertically, horizontally, and command C, command V, command V, command V. So is there. So what essentially we are doing here is that our domain is now broken into a series of nodes. Okay, in a series of volumes. Now you might get confused by the word volume, because in a 1D sense, what is essentially volume? Do we always have a volume there? Well, no. But volume means that now, uh, so let me write that. So finite difference. So finite volume method, the name finite volume might be misleading in the sense that there is no problem, might not be TD. Okay. So the name finite volume might be misleading in the sense that might not be 3D. However, note uh, this perfectly. This uh, construct or this name perfectly differentiates it with other finite approximation themes. So let's see how. So what happens is the domain. Okay, what is domain? Domain is the region where your independent variables are defined. It might be a unsteady three-dimensional problem. So the volume will be a hypervolume, a four-dimensional volume. Okay, volume means region in the domain. So the domain is now divided into control volumes. Uh, is now let me put it discretized rather than divide, discretized into control volumes or smaller control um, regions, control regions. Okay. Um, this is a little different from a finite element where also you look at a control region, you look at a finite element. So there we call it as an element, where here we'll call it as a control volume, and we'll see what is the difference from between a control volume and a control element, or a finite element or a finite volume. Okay, so the difference is domain is discretized into control volume. So now every time so what you do is now the function now the function uh, theta of eta is not defined only at uh, is not only defined at a particular point, but in a closed volume. Okay, that is important. But again, finite volume method does not. It is important to note that finite volume method does not uh, has a continuous. What should I say? Continuous um, function representation in theta. So now let me tell you about this. So what you do is you say that. So what you do is. Okay, so what you do is now that you are in this volume kind of situation, there is still a challenge in how to solve this PDE. And the way you do it is you integrate it over this small volume to see. So let's integrate it over a control volume. So the domain is now discretized into control volumes. The function theta is now not defined only at a particular point, but in a closed volume. Uh, a small, let me write that, an integration over this control volume is the first step in this in solving the equation. Okay, so if we do that, if we integrate this, integrating, what essentially we'll get is over a control volume. So now let me first show that to you how a control volume will look. So in this control volume kind of situation, you note that you are somewhere here and this is your domain of integration or region of integration for that matter. Um, the way we do it is, again, I will have to point this command V. So let's say this is the ith control volume. Okay, just walk through with me with this one. We'll discuss exactly. We'll revisit what essentially is the essence of this method. And there will be a west phase and there will be a east phase. So let me point that out to west, and there's a east phase. We'll mark it as W rather than marking it as west, and there will be a east phase. Okay. So now with this, uh, this is the way we do it. So we integrate it over this small control volume on integration. So this is integration. Let me write it as west to east so that it makes sense for a it is a little clear. West to east, and this is again e to the power dx. Okay. So now if you do this, you write d theta by d eta or dx, sorry, is uh, so this is now a function, right? This is a functional form. This integration, uh, or let me point that to so if. So east face of ith volume and west face of ith volume. That is important. So that, let me mark that. So now this integration is an interesting integration. Depending on the local value inside this control volume, across this control volume, we can suppose a domain. We can assume a functional form. Okay, we can suppose how this e to the power x. We know this e to the power x, right? We have to approximate this integral. This is a known integral. We are not approximating anything for our theta value right now. So this can be a good. We have to approximate this properly. A good approximation can be e to the power x I delta x, right? So this is important. Any functional form gets integrated like this. So you suppose that your integration is your region is so small that any function will roughly be a constant there. Or you could have better approximated this e to the power x, so you could have made a better guess. That is something that you would have to do. Uh, but well. Important thing is in this case also we are essentially requiring theta I values at the center of these control volumes. Okay, so 6 is theta of eta is approximated by n uh, theta values associated with these volumes. Okay, now this theta value can be anywhere inside this control volume. This theta value has to be in the range. It has to be a value that is close to the actual functional value in this region, right? In this very small region, theta value is not supposed is we are assuming in this method actually builds up on or assumes that you are not going to essentially get affected a lot by this variation in the control volume, the theta variation in the control volume. So you can give a theta value associated with this control volume. Okay. Important note here is somewhere. So where the span of integration is multiplied. I'm reading from the paper. Uh, okay. So now at this point, we are going to apply mean value theorem. Okay, by the mean value theorem, the location I must lie within. So let me see what is the mean value theory. So here, actually,
I
we
think
invoke mean.
neighboring nodes need to be considered. For
Mhm.
neighboring nodes need to be considered, I think, for finding their derivatives.
No, 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 no. See, so the thing is, it's not about the. So we here actually, it's not about the neighboring nodes at this point. The neighboring node concept was actually in the finite difference scheme. Okay, so it was like this in the last time. I think you're referring about this, right? Right? Neighboring nodes, right? This was something. This was a philosophy of finite difference philosophy. Okay, in a finite volume philosophy, let me just state what essentially is going on. So we are going to first invoke mean value theorem to progress from here. Okay, so from going from this to this is an interesting thing. Okay, so let me because we are going, if we are trying to understand what is the difference, we need to go into the integrities of this difference between these two methods. Essentially, a lot of time finite difference is confused with finite volume. But if you want to clearly distinct, draw a clear distinction between the two, let's go into this mean value theorem and stuff. So mean value theorem is generally given by, it's a simple theorem, not nothing much. We just have to quickly uh, get its statement. So in a region, so see now, so let me just write that, let F be a region R. Actually, it's not R. It's this. Yeah. So R be a continuous function, and the closed interval continuous. What is wrong with continuous? Spelling. No, continuous. What's wrong? Okay. On the It's a continuous function uh, and differentiable on where then such that, so let me write this, f of c, f dash of c is f of p minus f of a. This is something that we already know. This is a 10th level or 12th level. This is a 12th level thing there. One more thing is, what is the integral form of this equation? So yeah. So now essentially, just give me a second. Okay. So to make this approximation, see. So to make this approximation, what was the approximation we made? That, yeah, this xi should be between, so what x, so then, so for this to hold, then this is a simple stuff. Let me write this, that xi should lie between, is this line for line, should lie between x west of I and x of east of I. Okay. The important thing here is, it should not be it should not be the boundary points, or it should not be the boundary locations of the control variable. It is important. It should be somewhere in between. Okay. So generally, we can take it at the middle point, at midpoint. Otherwise, it is up to us. Take it anywhere in between this control volume, but just for a matter of convenience, or to be a very obvious, we can take it at center. Okay. Let me just point this out. So it is worth pointing out the location xi can be anywhere inside. A practice that is often preached in heat transfer text and many journal publication is finite volume node is often placed at the boundaries of the control volume. So we should not do that. We should not place it at the boundaries. This is mathematically incorrect. The most common practice to choose is the geometric center of the control volume. So as I said, if your space is two-dimensional or three-dimensional, you choose the geometric center. Okay. Um, okay. So now, okay. So now, wait a second. Right. So I think this is what you were pointing out, that we need to approximate. I see now your point, that we essentially now need to substitute these terms, and we'll use boundary nodes to approximate them, just like in the finite difference game. That's true. So what we are going to write here is, let me write that down. So theta I minus 1, um, theta I minus 1, or theta I, or let me write this. I minus I plus 1. I think I made a blunder there. You were right. You were right. We need to, in this case also, we will take the help of boundary nodes or the left and right values to approximate these fluxes. Okay. But there is an important catch there. Okay. Which I actually forgot to mention. So I'll quickly mention that also. So this is okay. And then the west, this is the east one. My mistake, this should be the west one. East one will be I plus 1 beta I and x. Okay. Now let's substitute that here. Okay. So essentially what we have done is that we take now rather than representing uh, so essentially what we have done is, let me draw the picture here. Okay. So this is our finite volume scheme. Okay. Just because you're there with me, Apur, can you let me know if you see a very sharp, if you see a clear distinction between the two strategies, at least in the picture format, in at least in the conceptually, what is going on, what is the difference there? Just because you're there with me.
So here we are considering smaller pieces of, I mean, if this is a 1D system, so we are, if suppose it is a like 1D rod, so we are considering small piece of rod as a control
Yes.
volume.
Yes. But how is it how if you just compare these two pictures, the finite volume and finite difference, do you see a difference, a striking difference between, because see, essentially what you were saying was correct, right? We are using approximate, see what we did there, the approximate. So what do I essentially mean is what am I trying to do there? So what was the essential principle of finite difference? Finite difference was that we simply what did we do was we simply approximated the second derivative, uh, approximated it as using Taylor series. That is what we did, right? So this was a finite difference. What we did was using Taylor series directly. Now comes the case of finite volume. Finite volume, although it is not clear here, but the step one is integrate, volume integration. Let me write that down. That is our first uh, step. This is the step one. Step two is, because you, as a consequence of the integration, you're going to get this stuff. Okay. Now let me do one more step and show that to you, that if I substitute these things in here, let's see what comes. Let's do that first. Okay. So if I do this, then I substitute this term. So as a second step, what we are going to get is, see, I'm not going to write it now because I've already written it. What I'm going to just, if you can just note that, you're going to get this. The same equation we got. Let me point that out. The same equation we got with finite difference. So now I
So
ask you.
So one minute, sir. The first equation in the box, I think in the second term it should be theta I minus theta I minus 1. If
Yes, yes, yes. That's right. That's right. But now do you see that the two expressions are the same, right? Right?
yes, sir, yes, sir.
But then, if I say so, I am being inconsistent because I'm saying this is a totally different method. Because now, first of all, we have integrated and then approximated. Whereas instead of directly approximating, we have used volume integration and then approximated it. So let me write this part using Taylor series. Why then fundamentally will finite volume be different from finite difference? Can you guess, or can you see why? Uh, Another important one more thing is, just let me think. So the same equation we got a finite difference.
Maybe the RHS, because of the RHS.
Yeah, so the RHS was also the same. So let's see. See, RHS was also same in this finite difference, e to the power xi. RHS was also same. Okay. Uh, the expression is also same. And this, yeah, this is this is why fundamentally a lot of time people confuses between the two methods, because essentially it might seem that we are solving the same equation, but we are not. That is the catch there. And the catch, I'll show it to you again. It's actually nice to be able to appreciate that. Look at this construction. It's a matter of how are we approximating our function. Essentially, what are we doing? We are approximating theta I by some theta I values, right? Right? That is what we are doing. We'll see that in the finite approximation setting, finite element setting, that is not what we are going to do. But in these two settings, at least we have a set of theta I values that we are using to approximate. Now, just looking at these two graphs, or do you understand these are not graphs. Do you understand these two schematics? Do you see what they're trying to signify? What are these black dots that are there on the number line?
Black dots are the places where we want to measure the quantity.
Yeah, so these are the points where theta I values will be estimated, right? Calculated, or this is where we want the theta I values. In the finite volume method, just look at how theta I equals to 1 is not at the boundary, right? It is not at the boundary, right? But it is at the center of a control volume which touches the boundary of your domain or of your domain, right?
Yes, sir.
And that makes a big difference there. We'll see why. Okay, we'll see why. If you remember, I can give you a hint why this will make a difference. If you remember, there was a question asked and also a point importantly raised in when we're discussing finite difference was that how do we take care of boundary points? This equation requires you to have this what do you say, theta I value of I minus 1 and theta I value of I plus 1. How do you deal with this in the finite difference scheme? And better, let's first discuss how do we discuss in the finite volume scheme. So to answer that, let me first say that this is not a fundamental equation, the same equation we got with finite difference, but this formulation is not fundamental to finite volume. Okay, what is the fundamental equation? Now, I am using a lot of jargons or just overemphasizing things here, but let's appreciate that. See, uh, I'm saying this equation is the fundamental equation of finite volume methods. Okay, and the equation that we have got after the Taylor series approximation is not important. It's a It's a secondary form. Okay, I'll tell you why I'm saying this. Essentially, this is the equation that we are trying to solve. First of all, we are not interested in how do we approximate these delta theta by delta xi's. This is one way of doing it. Okay, this is the simplest way of doing it. But this is the fundamental equation of finite volume methods. This is not a finite. This is not. This is just a constant that we are using to approximate these values. Okay, I'll tell you why. I'll tell you what do I mean. Okay. Uh, in this form is fundamental to finite difference. Okay, because del square theta by del x square will always come, or at least in central difference schemes, it will come like this exactly at this point. This is the step one of finite difference scheme. Step one of finite volume method is this. How we proceed with to step two uh, is important, but how do I emphasize this more clearly? Mm, okay, so let me first proceed. Let me first proceed. So now what we do is let me rewrite this, or let me reframe this entire thing. Okay. So what essentially we are going to do is we are going to say that for every theta I value, let me remove this. We are going to say we are going to define three values. Okay, we are going to define three values. There is a east flux, or there are fluxes, right? There are fluxes. In finite volume, we conserve, or we ensure that the two control volumes always have the same flux. That is an important aspect of it. Whereas in finite difference, this is not maintained. That is the major difference between the two. I'll show it to you. Let me this, and rather than putting I, let me put it that theta I. Okay. So now suppose this same thing, it is I, west I, this should be east I, this should be west I plus 1, this should be theta I plus 1, and this should be east I plus 1. Okay. The important thing here is um, to note, see, the important thing here to note is that while solving the equations for our theta I and theta I plus 1, what we'll ensure is that um, theta, this one, remains equal to, this is an important criteria in finite volume method. We ensure this to happen. Between two control volumes, we'll always ensure that this flux, this is a flux, right? This is a flux of, this is actually heat transfer. This theta was associated with the temperature. And we know from Fourier's law, Q equals to delta T by delta X. So that this actually will represent, in some sense, when you integrate the differential equation over volumes, you will get some flux terms. There will be some terms which will be leaving like crossing boundaries. These terms are called as fluxes. These terms are always maintained, or they are ensured that these two are same across two control volumes, whereas no such focus was given to fluxes when we were looking at finite difference. Now, as a secondary step, we write this as a secondary step. As a secondary step, we write this as, what do we write this as? We write it this way. And this will remain same for both ends, right? The way we have constructed this thing, this entire thing, for both of these, this quantity will be same. Now I'll show this how, like now it will become clear to you why this. So now I'll show it to you why this matters. See, first of all, in the finite difference scheme, there were no concept of fluxes. We were directly imposing this equation over all I values. But here we are ensuring between theta I equals to 1 and I equals to 2, the flux that crosses between these two control volumes remains the same. What that does to your numerical scheme is that you are now explicitly conserving your law. This will essentially be a conservation law, right? Here it is like heat conduction equation. So we are conserving Q in equals to Q out. And there is a temperature gradient kind of situation there. So heat, sorry, in here there is heat generation also. So heat in minus heat out is the heat generated term. This is what we are doing by ensuring this equation thing. This uh, uh, by ensuring this formulation, we are ensuring that the fluxes between two control volumes is maintained. So between this volume and this volume, um, you have the same flux. Now, that is essentially a major difference. I might not be able to justify or clearly show why. How does that make any difference? We'll see. The formulation will be a little different, but essentially across these small control volumes, we'll see that the locally the conservation law will get satisfied. So there is one thing that we'll see that. So wait. So there is one way to show how this affects the solution. Okay. So anyways, let's move forward. Okay. So we get to know that we are going to use these two terms to substitute this so that we'll get the same equation. But the interesting part here is earlier what we had done. The important thing is the important distinction also comes in the manner how we deal with the boundary nodes. How did we deal with the boundary nodes uh, in finite difference? Dealing with boundary nodes. We had we specified boundary uh, we specified boundary values, right? This is what we did, theta 0 and theta n. How do we deal with um, boundary nodes in finite volume method is very different. This is another place where the distinction becomes clearer. Okay. So what we do is we specify by boundary fluxes. Okay, this is what we do. We specify boundary fluxes rather than specifying theta. See, uh, we are given theta I values, right? We are given 0 and 1. We could simply say that theta 0 is 0 and theta 1 is 1. But you see how we have constructed our range. We do not, our theta I does not exist at theta x equals to 0. It does not exist at x equals to 0. It is existing at x equals to delta x by 2. And again, so there are no boundary. So theta I does not exist on boundaries. Okay, that is an important thing. Um, if that happens, see, if you shift your theta i's to the boundary, or if you shift the theta i's with delta x by 2, essentially you will go into the finite difference regime. How is that different? You will go into a finite difference scheme. And you also note here that for the same discretization, you will have an extra node in finite difference, right? This will be in plus 1 here. Here you have shifted a little bit, right? So you will have a one lesser theta value. So, but that does not matter. So now how do is we have to estimate. Now we actually need to estimate this rather than estimating theta I values. We need to we specify boundary fluxes based on based on boundary conditions. Boundary condition. So depending on how the boundary condition is specified, we'll specify delta theta by delta x. Suppose we were given a Newman boundary condition. You know about Newman boundary condition, Apur?
Yes, sir, the boundary condition is specified, right? I mean, theta is specified.
You know about, yeah, theta is specified. Do you know
Maybe-
about
maybe-
Dirichlet boundary condition and Newman boundary condition? Probably not.
I watched the videos. I mean, I've watched a few videos from week 4, week 5 also. Yeah. So
Okay,
Dirichlet
so
is
you
like,
know.
yes, yes.
Okay. So now if we were given a, we were would have, suppose we would have been given a Newman boundary conditions, then we could have directly specified theta west of 0 and theta of east of n plus n. But now we are given Dirichlet boundary conditions, or theta was specified. So how do we deal with that? We deal with that through this manner. Um, so we actually again use Taylor series expansion there, and we will use forward difference and backward difference kind of situation. So just to be able to do that, I actually will have to derive that. So let's do this. We'll have to see. So suppose theta of 0 or uh, theta of x1, okay, will be theta of 0 plus d theta by dx. This will be what? Can you tell me where will be at
Zero.
east of actually I put it at as uh, west of 1, sorry, west of 4. Right? Actually, I put it as 0, but it should be 1 or whatever. 0. X equals to 0 or 0. Yeah, you are right. Now, with delta x by 2, right? And I think we can also go ahead and write the second term. This should be double derivative. I'm actually, I could have directly written the entire thing. Not doing that because 6, 3 into 2, right?
So are you taking theta 0 as the boundary value? I mean,
Yes, because theta 0 is given to us, right?
yes, yes.
This, right? So now plus order of, so other terms which are cube in delta x. That makes sense, right? Right? Just let
Yes,
me
sir.
think. Let me see if this is how we do it. And yeah, and you can also write east of 1 and east of NC. 1 second. Mm, Yeah, we can also write this. Let me write this also. So the way we do it is there are multiple ways to do it, and depending on how you do it, your solution will change. So the way we do it here, just to show, is two forward and two backward Taylor series. Okay, so we use two forward series. So this you will write as 3x by 2, right? So let me, will be 6 and this will be 9. So what have I done is, let me show this to you. We remove this and this. Let this be west of 1, okay? This is theta 1. This is theta 2, right? What am I doing is, how am I writing this thing? See, this distance and this distance is delta x by 2 and 3 delta x by 2, right? I'm using this two concepts of Right. We actually need to do this only. This is our best option. This is our best bet. See, suppose I would have used this directly. Let's say if I would have not have gone for a two-step Taylor series and only a single step single step Taylor series, then what would have happened? This term, let's divide everything by delta x by 2. So what you would have gotten is you have gotten as this will be delta x 3, right? So you see, if I neglect this term, this term is actually linear in delta x. The error will be linear in delta x, which is not okay because this is a big error. At least we should have at least one order of magnitude difference, right? You cannot simply approximate this as, or just let me. See, so you see, actually the error will be a linear in delta x. At least we should go for delta x square. Okay, so we need two steps. Otherwise, we'll have issues. Or we could actually also try with this, see what happens, but there will be there can be large errors associated with this. So for just to be safer on a safer side, we go for a two-step method. So this will be delta x by 2. This is delta x by 2. This term is 3x by 2. Okay. Once we do that, can you give me the figure for can you using these two equations, can you find me an expression for this thing? Let's do this. We'll multiply the first equation by 3. No, not 3. Multiply it by 9, so the second terms get cancelled. So if you do this, what you have here is theta of x2, and then you subtract the thing. Okay. So if you subtract it, you will get theta of x1 9 times. 9 times because we are multiplying 9. See, I'm multiplying 9 so that this term gets cancelled. Okay. Then and then there will be so minus theta I, and then so this will be minus theta of 0 plus 9 of theta of 0, so minus uh, plus 8, I think. No, wait, yeah, plus 8 theta of 0, right? Then suppose when you tell me what will be the expression there, um, so this cancels and this one is 9, so 9 minus 3 is 6, 3 delta x. This will be 3 delta x. Can you tell me if this expression which I am going to write is okay or not?
Let
Okay.
me check, sir.
Yes, thank you. So meanwhile he does that, let's look at for the other edge, for the other edge. So in that case, you have theta of x n minus 1 and theta of x n minus 2. There the case will be theta of n. This is how you deal with if a Dirichlet boundary condition is given. You actually have to convert it as a Newman boundary condition. It's kind of this is what we're doing. So then you will have theta of n minus theta of east of n.
What if only Neumann boundary condition was there? How to deal with that?
Then we could have directly gone for the Newman boundary condition. Then we don't need to do all this.
No, means
Because this has
the node is
Mhm.
not at the boundary, right? The doubt, I have that doubt. I mean, the
Mhm.
node is away from the boundary, right? So
Right. Just
if the boundary condition,
let's look at what is going on there. Okay. So let's look at. So you're saying, suppose. So what are your boundary conditions you would like to give to me? Tell me. The theta
let
of.
it be theta naught something.
So delta theta by delta x is, let's say, 0. At where would you like to give it? At the right or left?
So I'm talking about Neumann boundary condition, just not
Which boundary
Dirichlet.
condition? Which
Neumann,
boundary condition?
Neumann, Neumann,
Yeah,
Neumann,
Neumann is this, no?
and
What is Neumann? What, what is Neumann boundary condition? Let's
I
look.
think Dirichlet is derivative, right?
No, 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 no. You're confusing. Let me check. Neumann boundary condition is this one. Or let me more clearly. See, we were given a Dirichlet boundary condition this time. Let's see. Dirichlet, see, this is the thing there.
Dirichlet is derivative, and Neumann is
No, no,
just.
no, no. No. Wait. Let me check then. Am I making any errors? Let me check. See, homogeneous Newman boundary condition at delta. These are the Newman boundary conditions, and these are Dirichlet boundary conditions. Let's look at more
Okay, so sorry,
clearly.
sorry.
Now let's check it properly. That should not be the case. So Dirichlet boundary condition is this one. Says that the value that the solution takes along the boundary is the fixed. Okay, so the value is fixed. Let's look at Newman boundary condition somewhere. Yeah, Newman boundary condition is when imposed on an ordinary, the condition specifies the value of the derivative. See, in the Newman boundary condition, the value of the derivative is applied, right?
Yes, yes. So I meant Dirichlet only, Dirichlet. I mean,
You meant
say like,
Dirichlet, which
yeah,
is the
like,
case we are having right now. So the boundary condition is theta of x is 0.
yes,
So
yes, Dirichlet.
theta of 0 actually. Let me say x equals to 0 is, let's say, 0. This is what the boundary condition we have right now. In which case, because our node is not at the boundary, as you mentioned correctly, what do we do? So this is what we do. We actually define this because see, essentially, as I told you, the fundamental finite volume equation is this. At boundaries, we are looking at fluxes. We are not looking at values. In a control volume setting, in a finite volume setting, we are not looking at edge values. We are looking at fluxes there. We're not interested in values at theta 0 or theta boundary. We are interested in the gradients there. And for that matter, we are doing this whole stuff because we know theta of 0, but we don't know what is this delta theta by delta x at that boundary. So that is what we do. Okay. I think it's clear now. I hope. And then this will be east of it's clear now, is it? Or no?
Yes, but how to apply in a code? I mean,
The code. I'll let you know. I'll let you know. So similar stuff. Let's see. This is the same thing. Can you just confirm that if this is fine or not? Same thing we'll do here. We'll multiply by 9. So this term gets cancelled. This entire terms get cancelled. This is what we want. So if we do this, what we will have is theta of x n minus 2, theta of x n. This should be theta of n actually. And this should be, just give me a second. Yeah. This should be theta of 1. Right. This should be xn minus 1. Yeah, this is okay. So theta of n minus 1 minus 1 minus. So now this time, yeah, minus n. That's okay. And then you will have plus 8 theta of 1. Should be east of. Yeah, actually there is an error here. This one is okay, but this one has an error. So what have I done here? You multiply 9 and you subtract this equation from this one. Subtract it, right? Okay, you subtract this one. So minus 9. Get this. This is
I think the signs will be reversed. Coefficients are okay, I think.
wait, just a second. Theta of x2. So it'll be, yeah, 3 minus, so this will be 3. Yeah, this is okay. They should be okay. What's the issue? Should I do it more properly? So this one is 9 minus 9. Hmm. I am theta. Theta. Should be minus. This is the issue there. Can you check once? Can you check? This is plus and minus. Uh, or should let me do it properly, yaar.
I think
Let me
it
do
should
it
be 9
properly.
theta x1
Mhm.
minus theta x2 minus 8 theta naught, something like that.
So let's do it properly. I'm not doing it properly. That's the issue. So equations are fine. Let's agree on that first. Equations are okay.
Ah, yes, sir.
Okay. Then this is 1, or let me say A, and this is. So we'll quickly see how to integrate this before the class, before we run out of time. We'll quickly see how to integrate this also. Not an issue. Now what I'm saying is 9 times A minus, so wait. So B minus 9A. This is what I'm saying. Okay, so if I do that, what do we have? We have theta of x2 minus 9 theta of x1 equals to theta of 0. Then I take a bracket, 1 minus 9. Then I take this term. I just take this delta x instead of delta x by 2. So what I get here is 9 by 2 minus 3 by 2, right? Which is 9 minus 3 by 2 plus some higher order terms. Plus some higher order terms. We'll not take care of those. Okay, now this is simple. Yeah, and this should be plus only, right? Because there is minus 8. Now this is fine, right? Do you agree with me now? Is this okay? I think this is fine. Take your time. Let's look at the second one. The second one, you write it as theta, and this is again T, and this is T. So what am I writing? D minus 9. So essentially getting 9. Did you check? Is this okay? Seems okay to me. That's okay. That's fine. Let me come back to this one. This is minus this one. Then on the other end, you get theta of 1 minus 9, theta of 1, 1 minus 9 again. And then here we write, yeah, there is this catch which I was trying to see. What is the catch there? Simple stuff. You will get 1 minus, so 3 by 2, 3 by 2 minus 9 by 2. Oh, shit, I see where I made my mistake there. So this is 3 by 2 minus 9 by 2, not, yeah. So with that, do we have here, you will get a negative sign, right? As you said, this should be 9 plus 9 theta minus theta of x, x2, right? That's correct. This is what we'll get. I had written it incorrect. You're right. Plus 8, no? Minus 8. Then on this end, you write 3 by 2 plus higher order terms. Again, not going to care about the higher order terms right now. In that case, what you have here is theta of I. This is minus 3, so you will get plus, minus, and this will be plus. Minus 8, so it goes to plus. Let me take this minus inside. So that. Now what do we have? Theta of x. Yeah, this is okay. Basically, essentially getting these two terms. Fine. So now we have these two equations for these two terms. Okay. What else? And so if we substitute these, so now we need to substitute. And so let's substitute here. Theta of 0 is 0. So this one gets like this. And this one will become, let me do it here. So, yeah. So now let's substitute these two values also. So this will go off. This will be 8, directly 8. Okay. Now, yeah. So now we need to substitute that in the governing equation to get a to how this is how you deal with it, deal with the boundary nodes. Okay, you need to substitute these things back in there. So if you do this, let me substitute this here. This will be west of 1. This will be x1. And what will this value be? Can you tell, Vapur? Can you tell me what this value be if we are looking at I equals to 1? So for I equals to 1, for interior faces, we saw what we need to do. For interior faces, we need to do this. To do this. So this is what we need to do. Actually, correctly written this thing down. So this was the initial equation. And this is what you do. Theta of 2, theta of 1. You know what I is? X1 is? We'll see. So let me just take 3 there. This is minus. So let me do this plus. So get this. Then we'll have these terms also. Then you have 12 here. Wait. Yes, 12, and there you get as 4. That's okay. And what is our x1 value? What is our x1 value? Let's look at. So x1 is delta x by 2, right? You get that, right? I hope that is clear. Anyways,
Yes.
for I equals to n, we'll do the same thing. Now we know about the west value, which will be what? We'll take from the here. West value will be this. Yeah, I made a mistake. Why am I making so many mistakes today? Let's redo this. There is an issue there. So theta of west I was this. Theta of east I we have to substitute. That was the interior face. West I was not the interior face. This will be theta of 1. Theta of 2 minus theta of 1 minus the term we arrived at, which is this value, equals to 3 to the power of x by 2 by 2. This should be theta of 2. This should be theta of 1. Now if I do this, I take the minus sign inside. So I get this. Then I take these two terms also in the same numerator. So I get, what do I get? 3 and 3. What that makes is you get a 4 here, so that you can remove this. This will be 12. Now let me check if this is okay or if this is wrong. This is the same thing we got, right? Yeah, this is the same thing. East was known. 1 was 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 Yeah, east was known, west was, this should be okay. This okay. Mm, let me proceed. Yeah, this is fine. Just a small issue. Yes, this is okay. Now going back, now we don't know the east part. So let me, before doing the east thing, let me put it as n and n minus 1. And then this should be what? This should be 1 minus delta x x by 2. Okay. Mm, hmm. Fine. And then we will substitute this back in here. Minus this one. Again, these minus sign I'll absorb inside first and then take it on the fraction term. This will be 3. This will also be 3. So this should be theta n. This should be theta n minus 1. So now this becomes 4 and this becomes 12. Okay. So now let me just check. So you get, it's okay, minus theta of n and minus, yeah, good. So these are the two equations we'll get for the boundary volumes. Okay. I'm using the word boundary volumes. For the interior volumes, we already have this. Okay. And now numerically, you can just see that it now differs from finite difference, because at the boundary, you are not saying that theta of 0 is 0, but instead you're imposing these two uh, linear equations. Now, just to answer Apur, your question, that this at this point your question gets answered, because now we have our equations, n equations and n unknown kind of situations. We just now need to remake our a and b files, a and b matrices, and that will give us our theta values. So this is what we need to do. Okay. um okay, so let's implement that today. So let me make a copy of this, or let me make it here only. 12th December. This, let's do redo this kind of certain stuff. So let me copy how much in here. Okay, let's go. Okay. Okay. So now we are looking at finite volume method. Okay. Now let's take an n as some 10 values. Here also I'll take 5 or 10. Let's say 5. We do this. In the finite volume scheme, we need exactly n volumes. So no need of n plus 1 here. Then del x, what will our del x be? Can you tell me what del x will be? It will be this divided by 2 also. That's important, because our del x, delta x will be actually, actually I should not put this. It's important to how to define how do we define a delta x? So delta x is essentially defined by this only, this length, but our value, our positions are starts from delta x by 2. So that is important to do. Now x should not, so x should be x plus del x by 2. Apur, please let me know if you get that right. See, this is wrong. This should be n, if I'm taking 5 points 0 to 1, and then you take n-1 points. Is it? No, not what you do.
I think it already accounts for that, right? If we take n, so it goes up to n minus 1 in Python.
No, what are you saying? Saying so 0.2 is del x. It should go 0.1, then 0.3, and so on. So it should be 0 to 1. How many volumes? It's actually starting from there. Okay, so let me do it this way. Should be like this. Del x by 2, 1 minus del x by 2. Let's see. Yeah, this is correct. You get this, right? So n points, n nodes. So let me plot this. PLT dot scatter. Um, dot fill space. Well, there's no need to plot it. It's essentially our x values will be at the nodes, right? So del x is 0.2, so our first nodes will be at 0.1, then 0.3 and 0.5 and so on. Our last nodes, the edges will be at 1 and 0.8. Okay. Anyways, then we don't have theta 0 is 0. This is fine. A and B you construct. That's also okay. Then your theta values is this. Now what you do is, how do you implement this? Let's look at how do we implement this. Okay. Um, Suppose this is a general case, then you implement this only, right? The earlier scheme that we used. It's just our B value will change. So our B value will change. How does the B value changes? B value changes like depending on our xi value. So it has to be this is del x square exi xi. This scheme we are using to represent this equation. Okay, interior nodes. Let me write that. If I is 0, if I is in 0, then we have a different situation. What do we have? If I equals to 0, the coefficient we have there is, so let's first fix bi. Let's start with bi. You're able to follow me, Apurv, whatever I have done in this box, or is it difficult to follow?
Box sensor is okay, so
Box is okay. Otherwise, you're having trouble anywhere.
in the code, sir, in the
Which one? Which one? Tell me. Tell me.
like x equal to linspace, that third
Ah,
line, third line.
oh, you don't understand this, is it?
Yes.
Okay, okay. I'll tell you. Quickly tell you. Let me open this stuff. So what does this lens space do is, actually you can go ahead and read about this NumPy library. What it says is, you linearly construct a space which is equal. So what you do is what you do is, I'll tell you. I'll show it to you what linspace does for just to start with. np dot linspace 0 to 1 10. Okay, let me take 11 or let me take 3. So it starts from 0. It's basically you are dividing the space linearly, and how do you define the space? You start from 0, you end at 1, and how many number of points do you give in the space is 3. Okay. So in what happens with 5, you get this. You start with 0, 0.25, 0.5, 0.75, and 1. Now you understand what linspace is?
Yes, sir. The first entry was in the linspace was del x by 2. That is okay. Last one is also 1 minus del x by 2. That is also okay. And okay, why 1 minus del x by 2? Huh, that is fine. Okay, it should be n at the end. I mean,
Yeah, should it be an n? That's a good question. So let's look at here what is going to be. So suppose we are dividing the domain into three spaces. Let's say we are dividing the domain into three control volumes. So the first control volume, uh, well, let's take, I don't like 3. Let me take it as 4. If I divide it as 4, or let me divide it by 2 only. Two control volumes. So what do you think if you're dividing the space of 0 to 1, two control volumes? The two control volumes will share the edge where at x equals to half, right? So the setting I'm trying to establish is this. Oh, let me draw my own thing only. Yeah, let's see what is going on here. So let's say, so this will be 0, right? If we are breaking the control volume, if we are breaking the entire domain into n control volumes, what do you think the length will be? 1 by n, right?
yes.
So this starts at 0 and this ends at 1, and the length has to be 1 by n. Okay. And then because there are n control volumes, we will move from half. We have, because every control volume has one center. So it has to be n number of points. So that part of it gets explained why n has to be there. Do you get it?
Yes, yes,
You get it, right?
yes.
Yeah, the confusion is coming from the fact that earlier in the finite difference scheme, we were having an extra n plus 1 number of points to cover the entire space. We needed an extra node. In this one, we need less number of nodes. So in this one, let me continue. Let me go back and just uh, those two equations that we had derived. We'll have to implement them. Where were they? Yes, it is here. Let me increase the size. So let's write bi for the leftist control volume. So you write delta uh, xi into, actually, yeah. Let me do one more thing in both these equations. Let me take this delta x on the left hand side. So I get this, and let me divide this 3 by 4 by 3, and this should be 3. Similarly, this delta x, let me take it inside. It's just for the matter of, it's just re writing, nothing much there. 4 by 3. Now, now AI, you look at here, what is AI? It's minus 3, right? Here, the coefficient is minus 3. AI plus I plus 1, because there is no I minus 1 in this case. I plus 1 is 4 by 3. 4 by 3. And both will require this del x square thing, right? Is that okay? If else if I in n, Or you could have just said I'll say phi equals to n. And actually you don't need to run it to n plus 1 times. It will be run by n minus 1. This also you understand, right? Why I had did this change. Let me rewrite this entire thing. This time bi I and then I minus 1. What will be the bi value? Bi value will be this only. This is okay. So we don't need these two terms. Remove this. Then okay, an important thing is um, indeed we will, if I have to actually remove this, see this 8 by 3 has to go here. Okay. Okay. So now this should be b minus 8 by 3 del x square. Then theta of n should be 4 4. This should be 4 and this should be 4 by 3. Minus 4 minus 4 minus 8 by 3. That's fine. So this should run. Okay, let's see. Okay, this should be fine. Let me see. Okay. Now let me go ahead. Please bear with me. Okay. See, so now this works well. Let me plot it. Similar stuff. Okay. So this is how you do the finite difference method, finite volume method. Let me plot this. Important. Yeah. Now that we are ending the class today, I'm not going to spend more time on finite volume. Like, I will not spend more time in this. We'll close now. But in the remaining hours, what we'll do is we'll discuss uh, we'll compare finite volume and finite difference as well before starting the finite element method. Okay. So yeah, meet you next time. Let's close today. Okay.